Hello and welcome to the new podcast PLC2's Logic Lounge, the recently awarded #1 worldwide authorized training provider from AMD. Whether you are an engineer and working with FPGAs or you are a student embarking on your journey in hardware design, this podcast is exactly for you. Sit back, immerse yourself in the world of FPGAs and listen to our conversation today.
Welcome to the first podcast episode of PLC2. My name is Alexander Fleck and I am a trainer and long-term digital developer, and I'm also working for PLC2 as a consultant. We have just recently been awarded the AMD Worldwide ATP Award as the #1 training provider, and we try to explore new ways of bringing our expertise out to the world. So I'm sitting here with our founder and former senior manager, Eugen Krasse, who is actually here to talk from the basics up, everything that you need to know about digital design. Eugen, thank you for being with us today.
Hello, Alexander. Thank you very much for the introduction.
So we will be discussing overall basics of digital design with FPGAs, and we will be starting on the core issues that young, unexperienced developers may find. And I think it would be very interesting to know from you how your long-term experience actually worked out. Like, what is the most prominent things that people just don't do right in digital design?
Yeah, I have a very important question. One of the most common causes of errors is a missing or even incomplete simulation. So this means the function of the circuit, it's not really carried out. So we don't really understand, will my FPGA work or not? Also, the external peripheral components are not really modeled and or even partially modeled. So therefore, we cannot see the proper cooperation and the functioning, the communication between the peripheral component and the FPGA itself. And another very important cause of a malfunction are CDC error. You often don't think about these mistakes straight away. And so it's very important for us to understand this is a potential error. And also, a common mistake is a poor timing specification. This means we fail to specify our timing requirements for our FPGAs. Because we don't specify our timing requirements, we never know, will my FPGA work with the desired speed or not. So there are certain rules we need to follow.
Yeah, that seems like a very wide-ranging topic list at this point, but it is quite well worthwhile that we should go through that maybe bit by bit. So let me maybe start with the first issue that you were mentioning. Why and how should I actually carry out an FPGA simulation to get the things right?
Yes, simulation is a very, very important step in our design flow. This means when we are simulating the FPGAs, we usually proceed as follows. In the first step, we perform the simulation of the subcomponents. This simulation of the subcomponents may also already be using peripheral components, models of the peripheral components. For example, in order to model the subcomponents properly, we should consult the vendor datasheet information to model the functionality, but also to model the timing. And in the second step, we should perform the simulation of the complete FPGA. And in this case, of course, we should connect all the important peripheral components to my FPGAs and run the complete verification and simulation. For non-embedded design, this is usually not very difficult. This can be done very easy. But for embedded designs, which usually includes microplates or sync components, that could be more challenging. So in this case, we will potentially need to use XI VIP, verification IPs, and even get access to very, very high transaction levels.
Yeah, so that means in the end, you can bind everything together in the simulation, and hopefully you can cover everything that you would experience in the real world then already? Or do you think there's the second step already relates to physical behavior that may not be the same between functional simulation and real world? So that's the question about the CDCs and how can I actually really work on these kind of
Yes.
models?
Yes. CDC is a very important part of our proper design technique. In this case, a basic understanding of the CDC problem is needed, and we need also to understand how can we address this problem. And depending on the task you need to perform, we need to use different synchronization techniques inside our FPGA. The problem a little bit, a CDC error cannot be discovered by running a functional behavioral simulation, because in the behavioral simulation we are using so-called unit delay models and unit delay simulation. This means the data passes inside the FPGAs. They don't have any delays. So in this case, we cannot discover potential CDC error.
So this means in the end, it's design experience to really get these parts of the circuits correct. But in the end, when you say you cannot really cover everything in the functional simulation, what is the approach to really get the real world, say, timing and behavior of the whole circuit then really covered?
Yeah, in our design flow, after we describe the design, after we run the synthesis, we actually do the last step. It's the implementation, the physical implementation. After we finish the physical implementation, we will get all the information will be available for us. This means the data structure of the FPGA, as well as all the delay values associated with the logic components, lookup table slices, as well as data passes signals. So in this case, we could check for CDC errors by running a timing simulation, but with some limited results, because in some cases it's not really very simple by running a timing simulation to understand the cause of an error. So much better approach in this case would be to run the timing analysis, because the timing analysis will tell us exactly a potential CDC problem. And the good news, some tools like the Vivado design systems, they do have already a CDC checking tool implemented as part of the system.
So it would basically know about some of the CDC topologies and it will be able to check your own circuits for that. So it would finally really be able to qualify and help you with that. That's actually really a very important point, I guess. So in the end, when you're talking about timing constraints, you would not only discuss like these internal dependencies, but you would also cover the I/O level and the behavior towards your peripherals. So that's also part of the timing constraints, I guess.
Yes, it's a central point. Actually, this means talk about timing specification of PGAs. We really talk about two different aspects. The first aspect is to bring signals in to the FPGA inside. So this is called the I/O specification. So in order to do the I/O specification, we need exactly define all the timing requirements for the input signals. And at the same time, the opposite, we have to define and extract all the timing specification for the output signal, the signals we generate by the FPGA. Again, the one and only way in this case to do this timing specification correctly is you have to consult the vendor's data sheet. The second part of the timing specification is the internal operation. So by using the timing constraints, you have to specify what is the maximum frequency of the FPGA. You have to specify which signal passes are simply doesn't matter. So this means we need to specify a false pass, Or in some special cases, we need to specify, let's say, a multi-cycle path. This means we do have more than one clock cycle time to run through this path. So this means that is very, very important. And again, we need to learn how to do this, because an incomplete timing specification will lead to a FPGA which will not really functioning in the real application. But a little bit a disadvantage, if you would like to say this, to make really good timing specification, the developer, the designer must really exactly understand the internal function of the FPGAs. If you don't understand the internal function of FPGAs, it makes a timing specification almost impossible. So in this case, I don't really believe what some companies actually are doing, a split between the designer of the FPGA and the second designer who is actually designed the FPGA, sorry, the timing constraints. I don't think this will even work.
Okay. So that sounds really like a very interesting topic to explore as well. And I think you gave us quite a broad overview now over the most important topics. Maybe we will just recap. It's basically saying, like, you want to see the functional simulation first. You want to actually align your clock domain so that you get a proper operational handshake between them. And then you will finally embed it into your surroundings and define the corner performance parametrics, I think, with the timing constraints. So that's quite an impressive list of tasks. And I will basically for now say thank you very much, Eugen, for having you here. And we will be hopefully able to discuss some of these topics in the next few sessions. And we will definitely do that along the lines with other podcasts. So if you want to follow that, you can subscribe, and you can still read about all the things we were discussing along the show notes. Thank you very much for this first podcast of PLC2. We'll be following up with more interesting news. Bye.
Thank you very much, Alexander. Bye.